Assalamualaikum warahmatullahi wabarakatuh, and good day. Hello to all. Okay, this time around for chapter 4, I'll be taking over to give you the video lecture, especially on chapter 4, 5, 6, and 8. So without further ado, I would like to straight away start with our lecture. Chapter 4 is basically dealing with isothermal reactor design. The lesson outcome is, after completing chapter 4, you'll be able to describe the chemical reaction engineering algorithm that will allow you to solve chemical reaction engineering problem through logic rather than memorization. And you'll be able to size batch reactors, semi-batch reactors, CSTR, PFR, and PBR for isothermal operation given the rate law and feed condition. In this particular lecture, I will only cover on the design structure for isothermal reactors, and I would also cover on scaling up. So how does, for example, like if let's say we have a batch reactor, and then you want to scale it up to a CSTR or to a PFR, how do you do that? But before that, maybe a question for you is that, okay, if let's say we have a batch reactor, why does the flow reactor is preferred over batch reactor in most of the chemical industries? Okay, and what need to be done if we have lab scale data and we wanted to design the reactor for industry? So these two things I would like you to ponder upon before when we met again in the class. There are basically 5 step methods that you need to know in order for you to design an isothermal reactor. But before that, do you know what does it mean by isothermal? So these are also the things that I would like you to know, and we will ask you what is isothermal before we can proceed with all the exercise and examples. There are 5 methods in which that you need to master. The first one is basically on the mole balance and design equation. Second one is rate law, which you already covered. Mole balance and design equation is chapter 1. Rate law is in chapter 2. Stoichiometry in chapter 3. The idea right now in chapter 4 is all about application, where we are going to combine all the information that you have learned from mole balance, rate law, and stoichiometry. And we will also look into chapter 5, which is graphical method, numerical method. This is in all chapter 5. So as for now, we will be able to evaluate, when we already learned about chapter 1, chapter 2, and chapter 3, we should be able to attempt and design the reactor based on the information that we got earlier. With related to the chapter 1, we have already looked into mole balance on different type of reactor. For example, like PFR, CSTR, as well as batch reactor. And we met together at rate laws, where basically we also had learned about different type of rate laws, whether it is elementary or non-elementary. So you need to know what is it already based on the previous video and the discussions. And we also learn about setting up stoichiometric table, which can be divided into 2 types, whether it is a batch stoichiometric table, or is it a flow reactor type stoichiometric table. What is different between both is that for batch reactor, the concentration that you measure is basically the mole of A divided by capital V, which is the volume of the reactor. But in terms of measuring the concentration of species A in a flow system, then it depends on the molar flow rate of the species A divided by the volumetric flow rate. Okay, so which is small v. And we have learned that to measure our species, for example, Na equals to Na naught 1 minus x, and Fa equals to Fa naught 1 minus x. And then we also have learned that if let's say if let's say that we are dealing with the liquid phase, they have a constant flow rate. Similarly, for batch reactor, if let's say it is a constant volume, V is equals to V naught, and for the flow system, small v equals to small v naught. Alright? But then we also learn that if let's say there is a gas phase happen, there is a present of the gas phase, therefore there is a variable of flow rate in the flow reactor, which means that you have to introduce the expansion term epsilon, and you should know already right now how to calculate your expansion term epsilon. And similarly with batch reactor, we also introduce epsilon term, and therefore when you include in your final term on to calculate the concentration, you must include this particular term. So that makes a difference between the expansion when there is gas phase present and when there is only liquid phase. Once we combine all this kind of information, okay, so we have few steps that we will have to follow, which I will cover after this. In order for us to scale up liquid phase batch reactor data to the design of CSTR, we must make sure that there are two information that is required. First one is chemical kinetics, which is the rate constant K, as well as to make sure that when we collecting the information, it must also free from heat and mass transfer limitation. What does it mean by heat and mass transfer limitation? So we must make sure that when we're trying to collect the information, the kinetics, this must be free from any kind of limitation which involve with mass transfer and heat transfer. Only then our K that we collected from the experiment are considered as reliable information. If let's say we still have some mass transfer and heat transfer limitation, when we do the experimental work, this means that this particular K value that we got cannot be used in order for us to scale up our reactor. And all this experiment to get this particular data is usually done in batch reactor. For example, when we have day 1 in the lab, we use batch reactor like a small beaker, and then we do some experiment, and finally, voila, we got the K value. But then, this particular value, K value, it doesn't change with any type of reactor. So, when we want to upgrade it, we want to use a different type of reactor, which is flow reactor. But we can use the same K value to design our flow reactor. So that is why it is important for us. Normally, at experimental base, in the lab, we normally use batch reactor in order for us to collect some information about K. But we can also use flow reactor as long as that particular flow reactor fulfills certain condition, which I will cover in chapter 5. So, when we want to get the K value, this is very important, okay? In order for us to get the K value and to scale up the reactor, the first thing that we need to master is the mole balance, okay? For example, like we know that in a batch reactor, there is no in, then there is no out. So basically, we left with this particular term, and A naught dx by dt equals to negative RAV, which is the generation equals to the accumulation. So, you have to follow this particular step by step, alright, in order for you to get from dNA by dt towards the NA naught dx by dt. For example, like you have dNA by dt equals to RAV, but you know that information from the stoichiometric table, NA is equals to NA naught minus NA naught x divided by dt, which is equals to RAV. And you can further simplify it, and it becomes negative dNA naught x by dt, okay, equals to RAV. and you take out the n anode terms, and now n anode dx by dt equals to RAV, which you got this particular information. This is only valid for when there is a constant volume, V equals to V naught. So basically, you are left out only with dCA by dt equals to negative RA. Why? Because NA over V equals to CA. Okay. For the second step, okay, we have to know about, well, we already know about the mole balance. You already have simplified the terms such that you become dx by dt equals to negative RA over CA naught. But now, when we move to rate law, if let's say now we assume that we have second order reaction from A to B, which means that negative RA equals to KCA squared. Okay. And then when we move to chapter 3, which is on stoichiometry, you know that CA equals to NA naught over V naught equals to CA naught 1 minus X. And we need to combine all this information, alright, where you substitute these particular terms, CA naught 1 minus X, into here. Okay? You know that RA is equals to KCA square, and you know that CA equals to CA naught 1 minus X. So you substitute this particular information into CA squared, and that's where you got this particular term. And then you know that CA naught is here, so you left with CA naught. When you cancel out CA naught and CA naught, then basically you left out with KCA naught 1 minus X squared. So this is equals to dx by dt. The next term is basically you need to evaluate. This is what we're going to do in chapter 4, where you already have this particular term, dx divided by dt equals to KCA naught 1 minus X squared. Then when you rearrange the equation, it will become to dt equals to 1 over KCA naught integral of dx divided by 1 minus X squared. And finally, when you integrate these particular terms, you will end up from the residence time in a batch reactor equals to 1 over KCA naught X divided by 1 minus X. So from here, you can know already how to get your K value, because your TR become your X. Okay? And then the 1 over CA naught X divided by 1 minus X is basically become your Y. Okay? And then your K value become your M. As long as you arrange that time is here and 1 CA naught X over 1 minus X is here. But when we change the scale, the axis, then the slope will become 1 over K, as simple as that. Okay? So you need to be very careful where does the time is put, whether it on x-axis or it is put at y-axis. If it put on the y-axis, so 1 over K is the slope here. Okay. Similarly, for first order reaction, I would like you to try it yourself by basically substituting, now assuming that the rate law is first order. Okay, K equals to CA, negative RA equals to KCA. So you will get that instead of this particular term, 1 over CA naught X divided 1 minus X, you will end up get ln CA naught over CA. And basically the slope is 1 over K. Okay. So we have looked at the way how we can get the rate constant by doing some experiment. And then we have to know whether what type of order of reaction is that. Is it first order or is it second order? And how about you try for zero order as well? Try to put now negative RA equals to K. Okay, so you will get the graph that is required in order for you to determine what is the K value.